If my theory holds true, then the universe is a fractal of sorts, with infinite fractals within. All fractals behave and appear the same, but just in an order of magnitude difference. Perhaps we can integrate utilizing this fractal behavior and conduct it over a reduction in scale of orders of magnitude towards zero, as the fractal is infinite theoretically, but practically finite in calculations. This may allow for the accounting of more information while generalizing complexity and infinite data behavior. Data/behavior. By such, we could potentially predict interactions currently seen as chaotic, turbulent, or unpredictable, or at the very least improve the limit at where this happens with our abilities. Newton's fractal and Newton's method for solving roots or whatever. I watched a video by 3 Blue 1 Brown that kind of went into this, and I was like, whoa, basically. And so the sampling or picking of points until the root is found is the same as following the path of a given particle in a gravity well. The swapping of sides or the root or overshooting of a guess is the particle orbiting the gravity well. This is why infinite fractals and uncertainty are formed on the boundaries. We may be able to idealize these boundary fractals into infinitely small squares or infinitely thin bands that alternate between boundaries. It will not be perfect, but infinity is hard to work with. So pretty much what I'm saying here is that I was watching this video, and I had never heard of what this was, but apparently it has nothing actually to do with Newton. But basically you have 3 points on a line, right? And all you need is 3 points for this, but you could do it with more probably. And by trying to, solve the root or whatever, like, of a given equation, which in this case would be that this given equation would be the, either velocity or acceleration or something equation of a given mass, right? So if you take that value and you plug it in and you try and solve for the roots, right? And you use this method and you kind of guess, oh, is it over here? And if you track plotting it, you depending on where it is located, you can kind of map out this fractal of how it will behave depending on a given input based off of this equation. If you put it at a certain spot, given its initial conditions, it will eventually end up, kind of moving around, but you will be able to find out where everything ends up based off of these initial conditions. And the plot that you get, it turns out to be this amazing fractal that has fractals within fractals within fractals on these boundary lines, right? So what I'm saying is that is gravity. That's exactly how gravity would behave, right? And so these fractals that we're seeing, if we could figure out how to integrate these fractals to some degree, right? Because the equation is giving us these fractals, right? But I'm assuming you probably need a pretty high-powered computer to do this. Maybe you don't. Maybe the compute is not as complicated as I think it is in order to generate these models and these simulations that he was showing. But the thing is that I think that if you can take that and use it with gravity, and because gravity basically, according to me, runs everything, right? If gravity is basically the deciding factor of every interaction, you can use that and apply it to fluid mechanics and apply it to anything that you're what is going to happen here? If you can define the initial conditions or whatever for a situation, then you can utilize that to find out what's going to happen, right? And so what I'm saying here is that the reason why turbulence becomes a thing is because on these boundaries, we end up with these fractals where there are fractals within fractals. And so moving just a little bit in one direction or another completely changes where you're going to end up. But if we could plot, where, like, if we could find out where the turbulence begins, plot that boundary, right? We say, okay, this is the turbulence boundary, right? And then we put in, we put in this fractal here, and then all of a sudden we know exactly what the behavior of this flow is going to do when it hits this boundary, because we have, the fractal there. And so everything that hits here, it's going to do this, and then everything that hits over here is going to do, one of these, I don't know, right? And so we can apply that fractal, but then generalize it to a point that not necessarily it is perfect prediction, but it is more accurate, right? And so it just peels back the how much we consider to be turbulent and how much we consider to be, predictable, right? And I think that utilizing this, I haven't done the math to figure out how you would do it, right? A part of me thinks that maybe I will have to do that, but I'll put this video out here, so if someone wants to apply what I'm saying and try and do it, is a lot more experienced with the math, because I have to teach myself the proper math before I can do this, and I'm lazy, so I don't want to do that. I'm not a mathematician. It's not me. So yeah. Anyway, I think what you would need to do is basically generalize a fractal, like take that fractal behavior, generalize it to a certain degree. And by generalize it, basically, take a point and be like, okay, anything after this scale, how in integration, in theory, you're integrating towards infinity, right? Like, there's infinite slices. Basically, don't do that. Because if you do infinite slices, then you have infinite fractals to worry about, and that's too much information. There's no way. So you can't integrate towards infinity. So integrate towards a value, and I think that value, depending on what you're trying to do, would change, because in fluid mechanics, I think that you're going to want to go with something small, but not too small, right? Because of just the nature of how it is. But other things where it's like, what's the word? I don't know, like planetary orbits and like trying to predict orbits and stuff like that. That maybe you could go smaller, because it's there's one planet, right, compared to, like, you're looking at the motion of one planet compared to the motion of like a billion atoms. So you can get a little more precise and still not have as high of a calculation, not as difficult to compute. Whereas trying to compute it like 1 trillion atoms over an infinitely small slice, it's just, that's too much. It's too much. At least I think. Yeah, right. So first you would have to get the equation for the laminar flow. Then you would have to figure out or define the boundary for the turbulent flow. And then you would need to then basically lay that boundary line over your flow, like over the surface of your flow, and then depending on what you map out, basically, you can be like, okay, well, every molecule that goes into that area of the fractal is going to have this behavior, right? And you can predict that. And then the problem is that because this is why it gets really difficult, because in turbulent flow, it's not like you that works for like 5 seconds, not even 5 seconds. That works for like a few seconds, and then all of a sudden you get some chaos going on. And so what you need to do is basically it's not going to be simple necessarily. Like, it's not the kind of math you're doing in your head. Unless maybe someone can. I don't know. But you would want to simplify the fractal, right? You simplify the fractal surface, but then what you're doing is that you're going to want to integrate it over the entire length of the flow that you're trying to predict, right? So if you're in a pipe and then the flow becomes turbulent here, and then it comes out of the pipe over here, right? And you're trying to predict what this turbulent flow is going to be, then what you need to do is basically, like I said, define the boundary, right? And then find out what those conditions are for that flow, right? Now that you've, like, I think you should be able to, once, like, utilizing that fractal, you can then infer what the next fractal will look like, right? And then apply that layer, and then you just keep layering fractals down, and they're not all going to be the exact same thing. Like, you can't stack the same thing, because the initial conditions coming into the first, like right on the boundary, will not be the same as the conditions right after the boundary, right? So every single one will have to be calculated after you calculate the one in front of it, right? So you'll be like, okay, this is what the conditions are. And then, again, you'd have to set some scale of time to pass. So you're integrating you're integrating through slices of time. And so you're getting different equations for each slice of time. So you could say, okay, at 0.1 seconds, okay, that's my next slice. So because you could do infinite slices, but like, that's a lot. That's a lot. So you got to generalize it to simplify it down a little bit. And it may not be 100% accurate, but it should be close. Then again, the longer you go for, the worse it's going to be. So, do what you will, I guess, right? And so, basically you just have to kind of slice it up and then have like the fractals, calculate each fractal, slice it up. And then in theory, doing that, you should be able to predict exactly how the flow is going to come out. And if you can predict how, like, I don't know, like, what does turbulent flow look like? I don't know if it even really helps to predict exactly how the turbulent flow is going to look when it comes out, like, because it probably just looks turbulent. It doesn't really look anything like anything, maybe. So I don't know. But if you could do that, then you could potentially then study this behavior, right? Because then you're breaking it down. You're breaking down this behavior, and you're kind of, okay, so this is what happens at this point. This is what happens at this point. And then you could potentially design a pipe to tweak it so that the fractal that you want comes out. And with like computer and modeling and stuff, like with the right equations put in, I imagine you could literally like design a pipe to take a turbulent flow and laminarize it. But like, I don't know if that's something that's even needed. Like, is that something that's needed? I don't know. I have no idea. But I don't know. I feel like utilizing this concept, we can make things that we thought were unpredictable more predictable. Not completely predictable, but maybe more predictable, more accurate, less ambiguity. So, yeah, like I said, I'm not the mathematician. I don't think that, like I have a couple ideas where it's like, oh yeah, I just need to spend like a month or two figuring out and like truly understanding mathematics, and then I'll be able to do these calculations and write it out. And I really can't get myself to do it. It's just not, it's not for me. You know, I, I'm all for contemplating the theory and the abstract. That's easy. That's no problem. But actually doing the mathematics and like doing the rigorous calculations, oh man, no way. No way. I don't know. Maybe I'll do it. Maybe I'll buckle down and figure it out. But I don't know. I wouldn't hold your breath. It's just, I don't know. It's hard to get myself to do that. I don't know. I'm not actually that smart, right? So, you know. Anyway, peace out.